அப்படிலாம் எதுவும் பண்ணுவேனா? எனக்கு வந்து அன்னைக்கு நம்ம இது டிஸ்கஸ் பண்ணோம் இல்லையா, அதுக்கப்புறம் அப்படியே கையால எழுதிட்டு அப்படியே கொடுத்துட்டேன், அவ்வளவுதான். என்னத்த பெருசா கலக்க போறேன், நான் வேணா அதை அடிச்சு விடுறேன் பாத்துங்க.
நானும் முடிச்சிட்டேன் சார், ஸ்கேன் பண்ணி அனுப்பல, அவ்வளவுதான், முடிச்சாச்சு.
சரி சரி சரி. ஜெகன் ஒருத்தர் இருக்காரு, ஜாயின் பண்ணிட்டாரா?
ஜாயின் பண்ணிட்டாரு சார், ஆனா படிச்சிட்டு இருக்காரு நினைக்கிறேன்.
ஹலோ
ஜெகன் சார், குருஜி ரிப்ளை பண்ண மாட்டேங்கிறாரு, வேணுனே ரிப்ளை பண்ண மாட்டாரு.
ஓகே. எல்லாரும் முடிச்சிட்டாங்களாப்பா இது அசைன்மெண்ட்?
சார் நான் இனிமேல் தான் பண்ணணும்.
என்னப்பா முடிக்கலையா? இப்ப இன்னைக்கு எல்லாம் அடிச்சிருங்கப்பா, அது வெயிட் பண்ணிட்டு இருக்காரு அவரு. ஹலோ.
ஆமா சார், 12 o'clock end of the day.
அப்பா அதை அனுப்பிச்சு விட்டுருங்க. சரி, யாருக்காவது அசைன்மெண்ட் முடியலன்னு சொல்லுங்க, நான் என்னோட இதை அனுப்பிச்சு விடுறேன், நீங்க பாருங்க, உங்களுக்கு தேவைப்பட்டதான் புடிச்சு பண்ணுங்க.
ஓகே சார்.
சார் நேத்திக்கு டிஸ்கஸ் பண்ணிட்டீங்களா சார்? இது பேர் என்ன, ஆஃப்டர் கிளாஸ்?
நீங்க டிஸ்கஸ் பண்ணுவோம்ப்பா. நேத்து கொஞ்சம் தான் பண்ண, நீ இல்லன்றதால பண்ண முடியல.
என்ன டாபிக் நேத்திக்கு?
இன்னைக்கு அதான் அந்த கைனமெட்டிக்ஸ் தான், கைனமெட்டிக்ஸ் ஆஃப் தி ஃபியூல் தான் நீ கண்டினியூ பண்ணுவோம். அப்புறம் ஓவராலா என்னென்ன படிக்கணும்ன்றது பார்த்துட்டு வந்துடும்.
ஓகே ஓகே. அவர் இல்ல, அவர் பிளேஸ்ல இல்ல.
ஹலோ, நீங்க ஒரு 1 hour உட்காந்துருப்பா, 8:30 to 9:30 போதும். பண்ணிட்டு ஒரு ஓவராலா ஒரு சம்மரி மாதிரி பண்ணிட்டோம்னா ஈஸியா போயிடும்.
ஓகே ஓகே ஓகே.
Hello. Good evening to all of you.
Good evening, sir.
Good evening, sir. Good evening, sir. Good evening. Am I audible?
Yes, sir. Yes, sir. Yes.
Okay.
You're audible.
Okay, is my screen visible to you?
Yes, sir. Yes, sir.
Yes, sir. Okay. Please answer your attendance. Aditya Kumar. Aditya Kumar. Okay. Anand.
Yes, sir.
There is some feedback coming. Aditya Kumar is present. Okay. He didn't answer the attendance. Anand?
Present, sir.
Ananta Kumar?
Yes, sir.
Arnachalam?
Yes, sir. Present, sir.
Hasan?
Present, sir.
Hemant?
Present, sir.
Jagan?
Yes, sir.
Kesav Prasad?
Yes, sir.
Lakshmi Narayanan? Lakshmi Narayanan?
Present, sir.
Prabhakaran?
Present, sir.
Prem Vinayak?
Present, sir.
To suddenly tell
Abdul?
Unmute and mute. Oh, yes, sir.
Roshan?
Present, sir.
Sabish Kumar?
Present, sir.
Satish Kumar?
Present, sir.
Titus?
Recording. Present, sir.
Valish?
Yes, sir.
Vigneshwaran?
Present, sir.
Jayraj?
Present, sir.
Vikas,
Present, sir.
Vivekanand, Yadav,
Yes, sir.
Yuvraj,
Present, sir.
okay, fine. Could you please mute your mic? Okay, so Saturday is your exam, as you know. Come prepared for the exam. As I said, you can come with your calculator. Okay, come with your calculator and ID card. Those who are coming in person. 3 of you who are taking online mode, who are in, they will be taking exam in the online mode. I will send out the instructions to you shortly about the procedure for the exam. Okay, so as I said, the exam will be asked for 30 marks, and the contents you need to go through are chapter 1 and chapter 2. Chapter 1 primarily involves theory-based questions based on the concepts that we discuss in the class. Chapter 2, the questions will be involving some problems based on whatever concepts we have discussed. Okay, so it will be for 30 marks. There are no choices. You have to answer all the questions. Okay, in 50 minutes time. 50 minutes is a total duration. This is a standard practice we follow for all batches for the quiz, for conducting quiz. Okay. Any question? Whatever data you need, it will be provided in the question paper itself. No need to carry the table. Okay, but you need to carry your calculator. For answer scripts will be provided to you. No need to carry the answer scripts. That will be provided to you for those who are taking in person. For those who are taking online, you have to carry the answer scripts. Okay, and as I said, you need to check your internet connectivity. See that it is stable. The video should be on for the entire duration. Any questions related to the exam?
Sir, the video which is like we are talking now, so this type of video is okay, or I have to just show this thing
No,
also?
your background is blurred, right? So I said the background should not be blurred. You should not. Did you get what I am saying?
I got the points.
Okay.
So there should not be blurred background, right, sir?
Yes, there should not be any blurred background.
Right, sir.
Whatever I am saying is a standard practice that we follow for everyone. Okay. So these are the recommended standard practices for online mode of exam and in-person mode of exam. Whatever guidelines given to us, we are following.
So now I've cleared the background, so is it okay now? Like what I mean to say is?
Yeah, yes.
Okay, sir.
Okay.
Thank you, sir.
Any questions related to the exam? And today is the due date for submitting your assignment. Those who are yet to submit, please submit it by today. Okay. I think I have given enough time, a week time. That is a reasonably good time to submit, and there are only 5 questions. I have already discussed the procedure for those also. So those who have not yet submitted, please submit your assignment.
Once the class is over, I'll submit, sir, for sure.
What is it?
So once the class is over, you can submit it, right?
Okay. Yeah. Anytime
Yes, sir.
today.
Thank you, sir.
Yeah. Okay. Any questions related to the exam? Okay. So there are no questions.
Sir, one question. Sir, how? Hello.
Yeah. Please.
Am I audible, sir?
Yes.
Sir, like how many questions will be there for 30 marks?
No, I will see that it is answerable in 50 minutes. So don't worry about the number of questions.
Okay.
Total marks are 30. There are no choices. Total marks are 30. It will be answerable in 50 minutes. So, and you should also note here that in a relative grading system, this is not based on absolute grading. Okay, IITM follows relative grading. In the relative grading system, you need to respond quickly to the questions. What I'm saying is we need to pick S and A grade student, okay, out of the total number of students who are taking exam. That is what I mean by relative grading. So you should respond to the questions quickly. If you take more time to respond, then you run out of time. That is one of the things in relative grading based exams. So once you practice more and more, you will be able to quickly respond to the questions. Then you will be able to complete all the questions within the allotted time. If you take more time to think and write, you may run out of time. Okay.
Thank you, sir.
So it means you need to practice well so that you can quickly respond and answer all the questions in 50 minutes.
Yes, sir. Thank
The
you,
thing in a relative grading is you need to do well compared to others. It's not based on absolute marks. It's based on relative. How well you are doing compared to others will finally help you to come up with a grade, good grade. Okay.
Yes, sir. Thank you, sir.
Yeah, fine. So are there any other? Yeah, Sabish.
And the marking will be basis the like what I mean to say. If there are some calculation error, but the steps are right in that sense. So it will be considered.
For each step, there are marks. So don't only worry about the final answer. Your approach in solving the problem is more important than what you get finally as a final answer. We generally give more weightage for the approach rather than the final answer. For each and every step you write, there are marks.
Thank you so much, sir. Thank you so much. It's very clear now.
Yeah, yes. Sabish, you are asking something. Any problem? No, that's why I had this assignment problem, right? That is a problem for practice. Those are the problems for practice. You can look similar problems from any of the references. Fine. Okay. So let me start from where I left in the previous class. See, so far in this chapter 3, we have discussed about the overview of combustion process in SI engine. We are now discussing about SI engine. Then I will discuss CI engine combustion. In SI engine combustion, so far we discussed overview of the combustion process in SI engine. The last class we discussed different stages of combustion. Okay, so here we have understood that the combustion event in SI engine is not instantaneous as in Otto cycle. Rather, it is progressive. It happens in 3 distinct stages. The first one involves development of a stable flame. Second stage involves how the flame propagates across the combustion chamber. And the third stage involves flame termination or after burning. Okay, in the first stage, only 10% of the charge is burned. In the last stage, 10% of the charge is burned. Most of the charge is burned in the second stage, which is the flame propagation stage, wherein around 80% of the charge, total charge here refers to fuel air mixture that we inject into the engine based on the operating condition. So most of the charge is burnt in second stage, meaning most of the thermal energy release is happening during second stage. And we have also seen that during the second stage, maximum pressure is reached in the combustion chamber. And we have also discussed something called MBT timing, which is a maximum brake torque timing. Okay, this maximum brake torque timing is compromise between loss of expansion work and reduced compression work, as we discussed in the previous class. Okay, so we need to optimize this spark timing at each engine operating condition. We often use the word optimize, because any optimization is based on a trade-off between counteracting effects. Okay, so here when I say optimize spark timing, I just inform you that it is a compromise between the reduced compression work and loss of expansion work. Okay, so you cannot start the combustion event so early; it will result in more compression work. Compression work is a negative work because piston is doing work on the gas. Only during expansion process, gas is doing work on the piston, which is called positive. In an engine operating cycle, only during expansion stroke, there is a positive work. During rest of the time, piston is doing work on the gas, so it is negative. So MBT timing is fixed based on reduced compression work and loss of expansion work. Why I say loss of expansion work? Now, to avoid the compression work, to avoid high compression work, you are delaying the spark timing to some extent. That will also result in some loss of expansion work. Loss of expansion work, because any delay in giving the spark timing will result in Pmax moving away from top dead center during the expansion stroke. It will also reduce the magnitude of Pmax. So there is some loss of expansion work because of the delayed timing, but nevertheless you are reducing the compression work. So there is an optimal timing based on this trade-off that we need to look at when we run engine at different conditions. And this timing, whatever I say optimal, is dependent on engine load and speed condition. So it needs to be controlled. That's why you have a control unit in an engine. Both SI and CI engine have an electronic control unit. With the help of that electronic control unit, you have a feedback mechanism. You closely monitor the engine operating variable, and accordingly you fix the timing of the spark. Okay, so that is how we achieve best performance from the engine, by controlling the spark timing. So this is what we have discussed so far. Today I'm going to start these factors influencing different stages of combustion. As I said to you earlier, one of the objectives behind characterizing combustion in terms of different stages is to bring out the various factors. So when I say factors here, it refers to engine design based or operating condition based variables, and these variables help us to control the different stages of combustion. Now we are going to look at what are the variables, engine design based or operating variables, that influence the different stages of combustion. Once you have an understanding about this variable, you will be able to better control the combustion event. By doing that, you will be able to achieve better performance from the engine and also reduce the pollutant emission from the engine. As I said earlier, we only have two targets: one, to improve performance; second one, to reduce pollutant. Both of this depends on the combustion event. How well the combustion event happens in the engine is what is going to decide the performance of the engine as well as pollutant concentration from the engine, emitted from the engine. So towards that, we are now going to look at these factors, engine design and operating variables, that affect the stages of combustion. Whatever stages we have considered, we are going to now look at the factors that affect each of these stages. Okay, so the first stage of combustion, as we know, is a flame development period. Okay, flame development period. Let us consider this as FDP, flame development period. So you know this flame development period is concerned with developing a stable flame in the engine. Okay, so the flame has to be stable. It's not about initiating the combustion event and forming a flame. It's also about how stable the flame is. If the flame is not stable, the combustion event cannot sustain. Okay, so we have to ensure that the flame that is generated due to spark discharge is stable enough to carry forward the combustion event. So there is some time lapse in this, and that time lapse is referred to as a flame development time or flame development period. Okay, so the process involved in forming a stable flame is mostly a chemical process. We can say that it's a chemical process. Okay, and this process depends on pressure, temperature, and equivalence ratio of the charge contained in the spark plug location. So what I'm saying here is, so this is the electrode gap, spark plug electrode gap. This is where you are starting the combustion event. Okay, so when I say you are starting the combustion event, you are doing that by discharging electric spark. So you are discharging electric spark in this region between the two electrode, which is designated here as electrode gap. What you have here in this region, you have fuel or mixture contained in this region. The volume of this region is so small. I already told you, I've given some specific typical specifications of this electrode gap. This is less than 1 mm, generally less than 1 mm. Okay, it varies anywhere between 0.7 mm to 1.7 mm, and this needs to be optimized based on the type of SI engine. Okay, this is a range, normal range of the gap, electrode gap. So you have a small volume of fuel or mixture contained in this region, and this mixture is what is going to be ignited by discharging electric spark. So what I mean to say here is this time period, the time required for forming a stable flame is basically a chemical process that depends on the pressure, temperature, and equivalence ratio of the charge. Charge here refers to fuel or mixture. Equivalence ratio of the charge contained in this small region. So we have a small volume of fuel or mixture contained in the electrode gap. That is what is going to get ignited. That is what going to form a stable flame. Okay, the time required for forming a stable flame is dependent on these pressure, temperature, and equivalence ratio of the fuel or mixture contained in this region. Okay. Now with that understanding, we are now going to look at these variables or factors. The first one is fuel base. It is type of fuel, okay, that we use in SI engine. Different gasoline, different grade gasoline has different properties, right? One of the predominant property that affect the flame development period is octane number, because octane number is also a measure of, although we say that it is antenna quality, it's a measure of antenna quality. We know antenna quality and ignition quality are inversely proportional. So the time taken to form a stable flame is dependent on the fuel characteristic, primarily the octane number of the fuel. Okay. The second variable is fuel or equivalence ratio. As I just now said, this is one of the important variable that affects the development period, flame development period. Then we have compression ratio. Fuel or equivalence ratio is an operating variable. You can vary the equivalence ratio when the engine is running, okay, by varying the proportion of fuel and proportion of air. So phi is a variable. When the engine is running, you can vary the phi value by controlling the air mass and fuel mass. So it's an operating variable. Compression ratio, whether compression ratio is a design variable or operating variable?
It's a design variable.
Compression ratio is a design variable because this compression ratio, how we define, this is equal to total volume, which is a summation of clearance volume and displacement volume divided by clearance volume. That is how we define this compression ratio, total volume by clearance volume. So this clearance volume and displacement volume are fixed once you design the engine. So this is a design variable. Compression ratio is a design variable that is going to affect the flame development period. Then we have intake, charge, pressure, and temperature. Generally, in a SI engine, we inject a fuel or mixture under ambient condition. The pressure and temperature are ambient pressure and ambient temperature. And you know that the ambient pressure and temperature also varies. In India, it doesn't vary much, but it varies between summer and winter season. But in abroad, in Western countries, even within a day from morning till evening, there is a tremendous change in the ambient conditions, especially the temperature conditions are different. Okay, so it varies. Ambient condition also varies. So accordingly, intake, charge, pressure, and temperature that enter into the engine will also be dependent on the conditions, prevailing ambient conditions. We also use supercharger sometime. And why we use supercharger? What is the purpose of using supercharger?
To increase the volumetric efficiency.
To increase volumetric efficiency, we want to fill more. We want to fill more charge within the given. Could you please mute your mic? I'm getting some feedback. Okay, thank you. So we also use supercharger sometime, right, to increase volumetric efficiency. As you rightly said, we want to fill in more mass with a given volume. To do that, you are compressing the charge. We call it as a boost pressure. We slightly raise the pressure by using a compressor, which is what is a supercharger. Okay, so if you use a supercharger, the intake conditions are going to be different. You will have a higher intake pressure, charge pressure when you use a supercharger. Sometimes we also use heating system. If you use heating system, the intake temperature is going to be different. In abroad, in Western countries, as I said, the surrounding temperature will be very low under winter. Okay, in winter, the surrounding temperature may go as low as minus 30, minus 40, and so on. Okay, so the temperatures are very low, so they will have a heating system in the house as well as in the vehicle. Okay, without heating system, they cannot survive. Okay, that is unfortunately the situation that prevails due to very low ambient temperature. So if you use a heating element, if you use a heater in the intake system, then the temperature is going to be different. So based on whether you are using additional devices like a heater or a supercharger, the intake conditions are going to be different. Based on the ambient conditions, the intake conditions are going to be I mean pressure and temperature are going to be different. So this is again a variable based on the prevailing conditions and whether we use additional equipment or not. Then spark timing. Spark timing is also an operating variable. Just now I said that I talked about MBT timing, wherein we need to optimize the timing by using a control system. Spark timing will also affect the flame development period. Okay, the time required to form a stable flame is also dependent on spark timing, which is one of the important operating variable. Next, turbulence. Is the turbulence design variable or operating variable?
Design variable.
Design variable. Turbulence here refers to the fluid dynamics inside the engine cylinder based on how you design the combustion chamber. In the last part of the chapter, I'm going to show you typical designs, combustion chamber design. There we will discuss about how the design of combustion chamber affect the fluid motion and turbulence inside the combustion chamber. But nevertheless, this is a design variable, as you rightly said, because it depends on how we design the engine. Okay, based on how we shape the piston crown, based on how we shape the cylinder head. Okay, piston crown refers to the top portion of the piston. It can be flat, it can have different designs. Based on the piston crown design as well as the cylinder head design, the turbulence level in the engine cylinder is going to be different. So this is a design variable. This will affect the flame development time. That is where you are discharging electric spark to initiate or start the combustion. So this gap size is going to affect the flame development time. This is again a design variable because once for all this is fixed when you design the engine. You are not going to vary this electrode gap when you are running the engine. This is not an operating variable, rather it's a design variable. So these are the different engine design and operating variables that are affecting the flame development period. Now we will specifically look at what will happen to the flame development period. We will look at, in order to reduce the flame development period, how this variable should be. Okay, we understood that these are the variables that are going to affect the duration of the flame development period. Now let us look at if the flame development period has to be low, how this variable should be handled. Whether I'm going to go through one by one and discuss how this variable should be in order to reduce the flame development period. Now let us look at the fuel type. One of the important property of the fuel that affect the flame development period is octane number. Now in order to have a shorter flame development period, whether the octane number should be higher or lower?
It should be lower, sir, because multiple lower. Yes,
if octane number is lower, it means antenna quality is poor. In other words, ignition quality is better. If the fuel has better ignition quality, I can say that the flame development time or period is going to be less. So from the flame development period perspective, it's preferable to have a low octane number, but generally we don't go with this because octane has a more dominant effect on knocking. That is a primary consideration. So the effect of octane number on flame development period is generally less because you are discharging very high voltage electric spark. I have already told you that we are discharging almost 10 times higher thermal energy to initiate ignition. So fuel ignition quality doesn't play a big role here in SI engine, whereas it plays a big role in CI engine because CI engines are subjected to self-ignition, auto-ignition. Here ignition is through spark discharge and we are discharging very high thermal energy to ensure that the mixture ignite. So although this is what is the direction-wise trend, although we say that octane number, when it is lower, the flame development time is less, but we never prefer to use a low octane fuel in SI engine because that will have knocking. Okay, we generally go with high octane fuel because knocking is a more detrimental effect in SI engine rather than its effect on the flame development time, which is taken care by discharging high voltage electric spark, wherein we discharge almost 10 times higher thermal energy. So this is taken care. Okay, but what I am showing here is how the octane number affect the flame development time. The second variable is equivalence ratio, fuel or equivalence ratio. So if I have to reduce the flame development period, what should be the equivalence ratio? So when I say equivalence ratio, you have three options, you know, stoichiometry, lean or rich. So which one will have a shorter flame development time?
Slightly rich, sir. 1.1 equivalence ratio.
Slightly rich. Perfect. Slightly rich will result, why slightly rich will result in shorter flame development period?
Because you have taught us that so if he is equal to 1, that means the combustion is happening to be stoichiometric. But what happens is still there are some oxygen left in the mixture. So
Yes.
that is getting consumed just like lean, matlab rich mixture compared to stoichiometric.
Yeah. So eventually this will result in very high temperature. The mixture the mixture proportion that results in higher temperature is going to reduce the flame development time. Just now I said that it is a chemical process. It depends on the prevailing temperature, pressure, and equivalence ratio. So slightly rich mixture will result in higher temperature. Higher temperature will reduce the time required for developing a stable flame. So we prefer to have a slightly rich mixture from the perspective of reducing the flame development time. Compression ratio. So compression ratio should be higher or lower to reduce the flame development time.
It should be lower.
So it should be higher.
Should be higher. So I got both answers, higher and lower.
For higher, sir, I would say it will have to travel less. So
No, there is nothing related to travel here. We are talking about the time required for forming a flame, stable flame in the spark plug location. It is yet to travel or propagate across the combustion chamber. Okay, this is stage 1. Stage 1 is concerned with forming a stable flame.
It should be higher.
with higher compression ratio, it will have high temperature and pressure of air available.
We prefer to have a higher compression ratio. This will reduce the flame development period. Why? Because higher compression ratio leads to higher pressure, higher temperature. Okay, higher the compression ratio, the mixture in the spark plug location will have a higher pressure, higher temperature. This will reduce the flame development time. Okay, as simple as that. It's directly correlated. When the compression ratio is less, the mixture contained in the spark plug location, I'm talking about the mixture in this region. Mixture in this region. So mixture in this region will have a lower pressure and temperature. When I increase compression ratio, the mixture here will have a higher pressure, higher temperature. That will reduce the stable flame development time. Then we have this intake charge pressure and temperature. So it is directly correlated, as you know. When you have a higher intake charge pressure or higher temperature, the development time is going to be shorter. So flame development time is dependent or sensitive to pressure and temperature. If you induct charge at a higher pressure and higher temperature, the time taken for forming a stable flame is going to get down. Now the next one is spark timing. So when you talk about spark timing, there are two things that you always say. One is advancing the timing. Spark timing can be advanced, and other one is retarded. Retarded is also called delayed timing. Retarded or delayed. Now, which one will result in shorter flame development time? Advanced timing or retarded timing?
Advanced.
Why so?
So we are igniting at the maximum pressure and temperature.
Advanced timing will result in maximum in-cylinder temperature.
And that we are introducing the spark when the combustion chamber is having highest temperature, or when you are having a closer to CD.
Okay. Any other
I
answer?
think retarded will be better, sir, because at retarded timing, basically, the effective compression ratio at that time will be higher. So it will be good for flame to propagate in that.
No, again, don't talk about flame propagation here. It's only development.
Sorry, flame development. Sorry.
Always remember that it is whatever we are discussing now is stage 1, which is development.
So basically, at retired timing, the piston will be closer to 3DC. then you're giving the spark. So that means at that particular instant, compared to advanced timing, the CR will be higher. So hence it will be good for FDP condition there.
Yeah, perfect. So this is preferable from the perspective of reducing flame development period. Why? Because, so what I'm talking here, the reference is always compression TDC. When I say advanced spark timing, I'm discharging electric spark somewhere here. When I say retarded timing, I'm discharging electric spark somewhere here. So somewhere here in the sense the piston is located here at the time of spark discharge in the advanced case. In the retarded case, the piston is located here. Okay, piston is located here with reference to compression TDC point. Now, when you compare the effect of advanced or retarded timing in terms of the charge pressure and temperature, when you advance the spark timing, you are discharging electric spark at this point of time. Okay, so at this point of time, the compression, effective compression is relatively less. When you delay the spark discharge until this point of time, the piston would have moved to this end, right? Because of the piston movement to say case 2, this is case 1 and this is case 1, this is case 2. For case 2, you know that in-cylinder pressure and temperature will be, what will be in-cylinder pressure and temperature for case 2?
It will be higher, sir.
Obviously high. And this will also reflect in pressure and temperature of the charge contained in the electrode gap. So basically what you are doing is you are allowing more compression to happen before spark discharge by retarding or delaying the spark timing. By delaying the spark timing, you are allowing more compression of the charge inside the cylinder. That will increase in-cylinder pressure and temperature, which will also reflect in the charge pressure and temperature contained in the spark plug electrode gap. Because of higher pressure and temperature, the flame development period is going to come down. Okay, that is the effect of spark timing on the flame development time. Now let us look at turbulence. Turbulence is nothing but the fluid motion inside the engine cylinder. So do we prefer to have more turbulence or less turbulence at the time of spark discharge so as to reduce the flame development time?
It has to be more, sir.
It has to be more. Why do you think it has to be more?
So the air motion will be more, so that the mixing will be high. Your flame development time.
But at the time of flame development, if there is more turbulence, the heat loss will also be high, right? We want to form a stable flame. Suppose if the heat loss is high, I said that during spark discharge, we are discharging 10 times higher thermal energy, primarily because of the reason that the heat loss is initially very high. That's why we have a high factor of safety. Now, what will happen if the turbulence levels are high at the time of flame development? Any flame you take, when there is an appreciable fluid motion during the formation of the flame, what will happen to the flame? The flame is subjected to, when the flame is subjected to turbulence, what will happen to the stability of the flame?
It will get disturbed.
Stability will be poor, right? When there is appreciable turbulence, stability will be less, right? We don't want that. If stability is poor, it may result in flame quenching. Okay, so to reduce the flame development time, we don't want appreciable turbulence. Okay, turbulence level should be low or negligible. Then only you will get a shorter flame development period. Otherwise, the flame stability will be affected. It may take more time because of the heat loss, higher heat loss. Remember that higher the turbulence, heat loss is dependent on the turbulence level, because see, turbulence, when it is increased, heat loss will be high, especially by convective mode, right? Convective mode of heat transfer is dependent on HA and delta T. It depends on temperature gradient. It also depends on the heat transfer coefficient. This H is dependent on the velocity, prevailing fluid dynamics. Okay, higher velocity will promote more heat transfer, okay, by convective mode. So heat loss is dependent on turbulence. We don't want any appreciable turbulence, because otherwise you will have a higher heat loss, flame stability will be poor. It may take longer time to form a stable flame. That is one thing. In the worst case scenario, the flame may not even get developed completely. It may get quenched or extinguished because of the prevailing turbulence. So we don't want turbulence at the time of spark discharge. Generally, what is done is the spark plug is located in the cylinder head. There will be a small recess, something like this. right? We generally isolate the spark plug location from the rest of the cylinder because we don't want any appreciable turbulence in the spark plug location. So this is where the spark plug is located. So it is generally located with a small recess, something like this in the cylinder head, because we want to isolate the spark plug from the rest of the region where there is appreciable fluid motion. In this region, there will be appreciable fluid motion. We don't want that to happen around the spark plug so that the flame stability is better and flame takes lesser time for forming. Okay, so we don't want turbulence at the time of flame formation or development. Okay, that's why we generally do this practice of isolating the spark plug region from the rest of the region. So rest of the region has very high turbulence. Okay.
Sir, only one question, sir.
Yeah.
During suction stroke, the turbulence will be like we required to be higher side, or how it is it? Because we can understand during flame development period, it should be lower. But during suction time, what is the requirement, sir?
During suction, there is no role of turbulence here. Okay, turbulence will play a role only for flame propagation. Turbulence aids only during the propagation time. If there is no turbulence, the flame propagation time will be longer. Okay, that will have detrimental effect on the performance, engine performance. Turbulence helps only during the propagation time. It will help in propagating flame at a higher velocity. That is one thing. That is a physical effect. And second one, as some of you said, it will also enhance the mixing, fuel air mixing, and it will enhance mass diffusion.
Okay, okay. So, like one more follow-up question, sir. Like the turbulence at same diesel engine will be like the answer will be remain similar as that of here.
Turbulence in a diesel engine has a different consequence. There, the problem, more severe problem is mixing, because you give a very limited time for mixing, and the fuel is less volatile or low volatile fuel, diesel. So the severe problem in a diesel engine is air fuel mixing within the limited time that is available in engine operating cycle. So the turbulence helps in reducing the mixing time, fuel air mixing time. Here the turbulence helps in propagating the flame. There the turbulence helps in mixing fuel and air.
Yes, yes, yes.
Okay. Thanks. So the last one is electrode gap, spark plug electrode gap. So here we are talking about how much gap we need to give between the two electrodes. Okay. So here I have a central electrode, here I have another electrode. Okay, so we are talking about this electrode gap. How much gap it should be from the perspective of forming a stable flame, right? So this electrode gap has to be optimum size in order to have a shorter flame development period. This has to be less, this has to be optimum. It cannot be too small. It cannot be too large. The electrode gap needs to be optimized. It's one of the important design variable. So if it is too large, if the gap is too large, what will happen? You are containing more charge. If you contain more charge, what will happen to the process, flame development process?
It should be better, sir, because possibility of it will I would say help to build up a charge like a flame.
How it helps in forming a charge? You said it helps in forming a stable flame, right? How it helps in that?
Because it will have more mass fraction of particular that gap. More mass fraction of fuel will charge will burn. So
okay, so you are saying that I have more fuel here, more fuel or mixture here, so more mixture will burn. That helps in developing flame.
Right, sir. Right, sir. Right, sir.
Okay. Any other problem we will have if you have a too large gap?
The voltage will be less, as I would say. Like spark energy will be less.
Spark intensity. Spark intensity will be low.
Very good. This is what I was expecting. What will happen to spark intensity when you increase the distance between the two electrodes? It's going to come down, right? Because the charge that you contain between the electrode gap act as a resistance. Okay. Because of this resistance only, the thermal energy appears in the form of a spark. So if you increase the fuel air mixture quantity within the electrode gap, you are offering more resistance. When you are offering more resistance with a given same energy that is discharged, the intensity of the spark will be less. If you contain less charge, there will be less resistance. For the same amount of charge, discharge, energy discharge, the spark will be more intense. That is what you prefer from the perspective of developing a stable flame. You want an intense spark. Okay, as I said, we need to provide discharge more energy because of the heat loss that prevails in that region. Okay, so when you fill too much of fuel air mixture with a larger gap, you are going to have a large resistance in that region. Large resistance will affect the flame development because this will reduce the intensity of the spark. In other words, what you have to do is you have to increase the energy that is discharged when you contain more fuel air mixture, which you do not want to do because it's a energy penalty. Okay, so we don't want too large a gap from that perspective. Suppose if you, from that perspective, if you look at too small gap, if you reduce the gap so as to increase the spark intensity, what will happen? What problem you will have with too small gap?
Very less charge available for the.
Yes, you have a less charge, one problem. Second one, this less charge will be in contact with the solid boundaries, right? Electrode gap and nearby solid region. So there will be appreciable heat loss and the flame may get quenched. If it is too small, flame quenching will happen. This is a prevalent problem with a too small gap. Flame may get quenched because the content is less, thermal energy release is less with a less fuel air mixture. And second one is heat loss is also high. So because of this, we don't want too small gap or too large gap. We want a optimal gap. So that's why I say that this electrode gap needs to be optimized based on a given engine, SI engine. Okay, so as to get a shorter flame development period. So these are the variables that affect the first stage of SI engine combustion, which has to do with the time taken for developing a stable flame. The second one is an important stage of SI engine combustion because this is a flame propagation period. You know, in flame propagation period, 80% of the charge is burned. 80% of charge is burned during this period of time. And during this period of time, the peak pressure or maximum pressure in the engine happens. And that is what is converted into work, useful work. Right? From that perspective, we also discuss about MBT timing. So this period or stage is one of the most important stage in SI engine. So we need to look at the variables that affect this stage. Okay, so this stage, we can say that it controls power output because this is a period where Pmax is happening, maximum pressure is happening during this period. That is what is going to affect the power output. There are two parameters here. One is Pmax and the other one is occurrence of Pmax. The crank angle at which the Pmax happens will affect the power output, the magnitude and the timing. Both of this will affect the power output of the engine. Since 80% of the charge is burned, this is a period where this flame propagation period is what is resulting in the maximum pressure. And this controls the power output. This is also the period where knocking combustion or abnormal combustion eventually may result because of later on we will discuss about the mechanism behind knocking. Because in this period, since most of the charge is burned from the plot of flame travel distance, and flame travel time, whatever we discussed earlier, we have obtained a profile like this, right? So this is stage 2. During stage 2, the slope is steeper. Okay, so what is the slope we said? The slope is nothing but flame velocity. This is a region, so flame velocity is very high during the second stage. Because of this, most of the charge is burned. 80% of charge is burned during this stage. What is also happening during this period of time? Suppose if the burn rate is too high, it will reflect in the pressure profile. So the pressure profile will be somewhat steeper if the burn rate is high. If the burn rate is less, then the pressure profile will be looking like this. So the profile, pressure profile, especially the slope of the pressure profile. This is pressure versus crank angle. This is what I mean pressure profile. So the slope of the pressure profile is also dependent on rate of burning. Just now I said that the rate of burning is going to be high because you have a steep slope, meaning there is a high flame velocity. When the flame moves at very high velocity, it is going to burn more charge in a given time. Okay, that will also reflect in the pressure profile in terms of the slope of the profile. So it will be more steeper if the burn rate is very high. It will be less steeper if the burn rate is less. So the rate of pressure rise is also affected by the stage 2. Stage 2 of SI engine combustion affect power output because this is the time where Pmax is happening. It also affect the knocking or abnormal combustion because in this period of time you have dP by d theta. The slope is nothing but dP by d theta. This dP by d theta is a change in pressure with respect to crank angle that you take in x-axis, okay, and pressure is in y-axis, crank angle is in x-axis. dP by d theta is called pressure rise rate. So this rate of pressure rise is also important. We need to track this rate of pressure rise. Suppose if it is beyond a limit, it will translate into combustion noise. This will translate into vibration. So you know, in any engine, NVH characteristics are also important. Okay, and NVH characteristics are dependent on the dP by d theta value, pressurized rate value. So since in this second stage, most of the charge is born, it also affects the rate of pressure rise. Okay, so we need to keep a check on how this rate of pressure rise is, whether it is within a limit or whether it is too high. We don't want this to be too high. Okay, with a very high flame velocity, this dP by d theta will become too high. If it is too high, there will be combustion noise, vibration. It may also eventually lead to knocking kind of combustion. Okay, so this is an important stage of SI engine combustion because it affects power output. It also affects the rate of pressure rise and knocking. Now let us look at the variables that are going to affect the second stage, flame propagation stage. So we are looking at the engine design or operating variable that control the propagation period, flame propagation period. Basically, these are the variables that affect the flame velocity. You know, flame propagation is primarily dependent on the magnitude of the velocity, flame velocity. So this engine design or operating variables affect the flame velocity, thereby this second stage. The most important variable is turbulence. Okay, the turbulence level in the engine is going to affect the flame propagation speed. Okay, and thereby it affects the duration of the second stage of SI engine combustion. Second one is fuel air equivalence ratio. This turbulence is a design variable. Just now we discussed about that. The second one is fuel air equivalence ratio. This is an operating variable. Depending on the value, fuel air equivalence ratio value, meaning rich, lean, or stoichiometric proportion, the flame propagation velocity or the flame propagation speed is going to be dependent on. Okay, so earlier I said that SI engines generally have a very narrow equivalence ratio value close to stoichiometry. One of the reason is the flame stability will be poor otherwise. Flame propagation based combustion is what is happening in a SI engine. To have a stable flame, we need to keep a check on equivalence ratio, otherwise flame stability will be affected. So this is one of the important variables that affect the flame propagation period. Then we have compression ratio, which is a design variable. Intake charge, pressure and temperature will also affect the flame velocity because based on this, the prevailing pressure and temperature conditions in the engine are varying, and accordingly the flame propagation time is going to be different. Engine load, I will talk about the effect of engine load in detail in the next class. Engine load, low load or high load, the engine operating condition in terms of operating load is going to affect the flame propagation speed. Okay, generally at higher load, you will have a high flame propagation speed. At low load, you will have a low flame propagation speed. I will talk about the mechanism involved behind this in the next class. Engine speed directly affect the turbulence level in the engine. Higher the engine speed, higher will be turbulence level. Thereby, it affects the flame propagation period. The last one is size of the engine. Size of the engine here refers to bore and stroke, which are two important dimensions of an engine that affects the displacement volume. Engine size also affects the flame propagation speed. So this is again a design variable. We are going to see in the next class in detail about how this design variable affect the flame propagation period. So these are the important engine design or operating variable that are going to have an effect on the stage 2 of SI engine combustion, which has to do with the flame propagation period. So I'll give more finer details about how these variables affect flame propagation period in the next class. It's time up. I stop here. If you have questions, I can take your questions now.
Professor, this is regarding the previous classes note, like heating value at constant pressure. If you can open the slides, it will be great. I'm sorry to trouble you.
Heating value at what is it?
So constant pressure. From your notes, sir, I think it is 12 or 11, if I'm not wrong. So come down, sir, a bit. Exactly, so over here.
Okay.
So enthalpy of reactant is basically summation of number of moles into enthalpy of at standard condition, and then T0 to Ti.
Yes.
And then enthalpy of product is again same thing. Now, sir, if the reaction is happening at standard condition, suppose like at room temperature, then the sensible part of it, like T0 to Ti, that will become zero, no, sir, if I'm not wrong. If my understanding is correct.
Suppose if the initial temperature is equal to standard temperature.
Exactly.
Then there is no effect of sensible enthalpy.
So this will become zero, right, sir?
Yes, yes. It will be only enthalpy of formation because it is happening under standard condition.
Thank you so much. That was the confusion I had.
Okay.
Thank you, sir.
Yeah. Any other questions?
And sir, generally, sir, suppose if he asks to find, given a problem, if he asks to find the adiabatic flame temperature, we have to consider like constant volume reaction or constant pressure reaction.
That will be mentioned in the problem itself.
Okay. Okay.
Okay. Yes. Okay. Okay. Wattage of glow plug depends on the prevailing ambient condition. How intense the glow plug thermal energy you are, the wattage will decide the thermal energy that you are discharging through glow plug, right? That depends on the ambient conditions. It needs to be optimized based on the ambient condition, ambient pressure and temperature conditions. No, we need to do a detailed calculation here because wattage will decide the thermal energy that is discharged through the glow plug. Okay. So the thermal energy discharged through the glow plug depends on ambient pressure and temperature condition. It also depends on the capacity of the engine. Capacity of the engine will give you the m dot, right? Mass inside the engine, right? Maybe m itself, right? The total mass inside the engine is dependent on the capacity. Okay, and the specific heat of the charge is another variable, and then delta T is another variable. Q is mCp delta T. So the thermal energy you are discharging is basically this one, right? This much. And that is dependent on the mass, that is dependent on delta T, which depends on the ambient temperature and also depends on the charge. Charge here is primarily air, fuel mass is negligible compared to air mass. So these are the variables. These three variables will decide how much thermal energy you need to discharge. Yes. If you are able to bring it up to ambient, then the rest will be taken care by the system, whether it is self-ignition or spark discharge. Because we have a fuel with a well-defined ignition quality. So you know under what conditions that fuel will ignite with a given proportion of air. Okay, based on that, you need to take the charge to that level so that it can self-ignite in case of CA engine. Okay, fine. So it's time up. I stop here. I will meet you tomorrow. I will meet you on Saturday for the exam. The next class will be on Monday. Okay. Thank you.
So in case of any doubt, we'll reach to
the exam.
you.
Yeah, you can write email to me in case if you prepare and have doubt in any of the content, you write to me. I will get back to you.
Thanks.
Okay. So good luck with your exams. Thank you.
So thank you so much, sir.
Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you, sir.